This is Mr. Sitta, and I'm going to make sure it's set there. I want to do the key for the, I'll show you the solutions for the interactive lab on thermochemistry. What we did is we took water and we mixed it with the following, solid, and then these are two liquids. No, I was using a solid here. HCl is a liquid, and acetone is a liquid. Now, the masses, for the total mass, for all this, we're going to use Q equals Cp times the mass times delta T. And we're going to calculate the amount of heat. And the units are going to be in joules. The goal of this reaction is to find the delta H of solution, of dissolving it. So we want to find the delta H of the solution. So what it's going to be whatever our Q is, and then we have to change that to kJs. And it's going to be, we'll change the sign. The heat from the water comes from the dissolution. So if we looked at it as system and surroundings, the heat is going from the system into the surroundings. Well, we're checking the heat on the surroundings. So if this is our Q, this is going to be negative Q. The signs will be opposite. And we'll then divide that by moles of our solute. So we're going to find out the moles of solute and divide each one. Okay. The mass is the total mass. So when you take the solute and add it to the solvent, this is the mass of the solution, and that's what we want to use in the calorimetry equation, is the total mass of the solution, because everything's changing temperature, including the water. When we use moles, we don't use the 102. We're just going to use the moles of the solute particle. Okay, that gets confused. That's where a lot of people make mistakes. Okay, now I'm assuming this is all correct. A student had written this up, and this is what they got. You may have different numbers. They got an initial temperature of 20 and a final temperature of 24.8. So the temperature change, the delta T, is positive to the solution. Okay, so then 20 drop into 18.5, that's a negative 104. The temperature change here, it went up, so that's a positive. 20 to 25, that's a positive. 20 dropped down to 7, so that's a negative. And then this had to be an error, because I know acetone and water have a delta H of solution, but I think I would just ignore the last one, because it came out with no temperature change. So whatever happens, our delta H for this is going to be 0 kJs per mole. All right, so let's rock and roll for this one. Your CP for all of them are going to be 4.184, and that's joules per gram per degree Celsius. The mass is our total mass, so we're using the 102 grams. Grams cancels out, and we're using our delta T, which is 4.81 degrees Celsius. That cancels out. I might point out that this is a temperature change, so I could also use Kelvin, but I can't use Fahrenheit. Okay. So what do we have for a Q? 4.184 times 102 times 4.86. So the Q for this one equals 2074 joules. Now, I'm going to find the delta H for this. That's the next step. And as you went on the lab, you had an option to turn it on. For the solute, you could click on it and see the delta H, see the value actual. You could also look it up on YouTube. You could just go ahead and look it up on Google and search for it. Okay, the first thing I'm going to do is convert joules to kJs. So dividing it by 1,000, so this becomes 2.074 kJs. So the delta H, it's going to change from a positive to a negative. And this is the way I think of it. The temperature went up, so it's exothermic. So it's going to be negative 2.074 kJs. And I have to divide it by moles of KOH. So I'll take my 2 grams of KOH, gram to mole, it's 56.1. So 2 divided by 56.1, I get 0.0357 moles of KOH. And this is another way to get delta H. This isn't a reaction, we're just going to say of a solution. It's a change in enthalpy for making a solution. Okay, times 2.07. For this one, let me try that again. I got 58.0. Okay, kJ per mole. I think the value actual is 57.7 and it's negative. So how do I do percent error? Percent error equals value actual minus value experimental over value actual, absolute value times 100%. I know this is a negative, but I'll just say it's absolute value of everything. So if I use 57.7 as my actual minus 58, the difference is 0.03 divided by 57.7 times 100. So the percent error for this one, you're not getting near 100% error for any of these. When you plug it in this equation, you should have fairly low, even near 0% errors. So for this one, I'm really just getting 1 sig fig. So it's 0.5%. And this reaction, the temperature went up, so not endo, exothermic. The temperature went down, that's endo. Make sure you got the right concept here. This is temperature is positive, so it's going up, so that's exothermic. This temperature is also exothermic going up. And this one is neither, but this one is going down, so this one's endo. Okay. And I can now, if you do one good example, you can just run through the rest. This will be 102 times 4.184 times the temperature change is 1.5. So I got 640 joules. So I got 0.640 kJs. Now NH4NO3, 28 2 nitrogens plus 4 plus 48 for oxygen. That's 80 times 2. So 2 divided by 80. So I'm dividing this one by 0.025 moles. It's going to be exothermic, so it's going to be negative. I'm getting 25.6 for this one. And the unit is kJ per mole. So that one checks out. This problem, let's do this one last because it's totally different because I'm dealing with a solution. So I'll do that one last. I'll just check this one out. I know sodium hydroxide should be 44.4 as a value actual. The change in temperature is 5.21 times 4.184 times the mass, which is 2 grams, 102. 22,200 joules, 20 joules, divided by 1,000. So this one is negative 2.22. I'd say 3 sig figs right there. So that's the number of kJs, and for NaOH, I'll take 2 divided by 40, 0.05 moles times 2.22, 44.4. I get kJs per mole. The last one, glucose, 0.29. That's my temperature change times 102 times 4.184. That's 123 divided by 1,000. So that's going to be positive 0.124 kJs. Okay, and I'm going to use just 2 grams divided by 180, the molar mass. So the number of moles is 0.0111 moles. So this one I'm getting positive 11.2 kJs per mole. This one would have been 0, and let's come back to the HCl. Okay, for the HCl, I'm kind of writing these all over the place. And get a little neater. So for the hydrochloric acid, in most of these, I had water in a cup. I was measuring out 2 grams of the solid, and I was dumping the solid into there, and if it was exothermic, I was seeing the temperature, the Q, come out. If the temperature went down, if the temperature went down, if this was exothermic, the temperature rose. If it was endothermic, the heat went into it. Okay, so that's if your temperature dropped. So Q's either coming out or going in to the solution. This one's a little different because I have 2 cups, and I'm adding the 2 cups together. So I have a solution. So Q equals Cp times M times delta T. First of all, I added 100 milliliters plus 100 milliliters of solution. So the total mass, the total volume becomes 100 milliliters, and you have to know that 1 milliliter equals 1 gram for water, and we're going to assume that it's mainly water. So the 200 milliliters becomes 200 grams. So you got 4.184 grams, joules per gram per mole times 200 grams. Grams cancels out. That's per Kelvin. Yeah, not Kelvin, well, degrees Celsius. And then times the temperature change, which was 0.29. Now, 6.81 degrees Celsius. That cancels out temperature. Okay, so your heat, 4.184 times 200 times 6.81. The Q for this then is 56.99. Alright, sorry, just 56.99 joules. I'm going to convert the joules to kJs. So 1,000 equals 1, so it's 5.699 kJs. Now my delta H, the Q is negative divided by the moles of the NaOH. So negative 5.699. I know I got 4 sig figs down there. I'll cut it down after I do the moles. The question is, how do I get my moles of sodium hydroxide? Well, I have to use solutions. I know I have 100 milliliters of NaOH, and I want to find the number of moles of NaOH. So I'll convert a milliliter to a liter, dividing it by 1,000. And the molarity of this, it gives you as 1 molar. So 1 mole is to 1 liter. So what I end up with is 0.10 moles of sodium hydroxide. So I'm going to divide this number by 0.10 moles. And my answer, I'll now round it off. I'll say 57.0 kJ per mole. Now, why didn't that come out? Yeah, I should add. Well, it's not just dissolving NaOH. This is also, you have HCl reacting with NaOH. So for that reaction, that's for an overall reaction, not just sodium hydroxide. Okay? All right. That's pretty much the lab calcs.